All right, here we go. General Chemistry 2. There we go. I think we're okay as far as the technology today. Let's see. Looks like we're leaning a little bit. Nope. Guess that's just the way the projector is. Okay. Today is Wednesday, the 24th of February. And today we have a few announcements. I'm just going to mention, there are quite a few, so I'm going to go over them fairly quickly. ALEKS Chapter 15. We're going to cover Chapter 15 today and on Friday. At this point, it is due on Friday night for both sections, both the online and in-class section. Chapter 15, just the one ALEKS. We're going to cover half of it today in our lecture and then the other half on Friday. The goal is that we have OpenPI this weekend, so you can go back and work on anything you like. Make sure that you get caught up. Lab 3, so for those of you who have lab tomorrow, don't forget to be prepared for the nuclear chemistry lab. Quiz 3, it's open right now. You have 10 minutes to take quiz 3. It's 5 questions. It's on stuff we've been talking about recently. You have until tomorrow night to take the quiz. Plan for 10 minutes. Once you start, you need to take the whole thing. And it is due by midnight tomorrow night. So don't forget quiz 3. Worksheet 9. Now for my face-to-face class, we're going to do these. I'll collect them either today and Friday, probably today and Friday with worksheets 9 and 10. For the online class, make sure that you upload worksheet 9 by Thursday and make sure that you upload worksheet 10 by Saturday. Finally, in a couple weeks, we have exam 2. So something to look forward to. Oh, we have to have just a little bit of despair today. Sometimes the best solution to morale problems is just to fire all of the unhappy people. It's always darkest just before it goes pitch black. Speaking of which, go. Couple of Valentine's related ones. You were meant for me, perhaps as a punishment. Even the most ambitious little pebble will never grow up to be a big rock. Ooh, that's harsh. You are the wind beneath my wings, otherwise known as turbulence. Because there's nothing standing between you and your goal but a total lack of talent and a complete failure of will. Ouch. Poor little goldfish. It takes months to find a customer, but only seconds to lose one. The good news is we should run out of them in no time. Another business-related one. And finally, one of my favorites, there comes a time when every team must learn to make individual sacrifices. All right, chapter 15, thermodynamics. So what we're going to be talking about today, the first half of the chapter relates to entropy. So here's what we're going to be looking at throughout chapter 15. Understanding spontaneous processes, what entropy is, and entropy changes in a system. So that's actually just for today. We're going to do all of these. So as a reminder, this is what we've been going through in chapter 14 with kinetics. With kinetics, it predicts how fast a reaction is going to go. You have the hill, the activation energy, and how molecules interact to make that reaction go. Thermodynamics, on the other hand, just predicts whether it's spontaneous or not. Thermodynamics says how much energy is involved in this process overall. Thermodynamics doesn't care how you get there. So, the world of kinetics is in between these two blue lines. It has to do with activation energy forward, activation energy reverse, any transition states, any intermediates. Thermodynamics, on the other hand, is the difference in energies between reactants and products. Thermodynamics doesn't care about this hill. All right, spontaneous versus non-spontaneous. A spontaneous process is one that naturally occurs, and a non-spontaneous one is one that does not naturally occur. That may be obvious or self-evident. Well, sometimes there are processes that want to happen, but they may not. There are other reasons why they may not. For example, there could be a high activation energy, but a spontaneous process is one that generally wants to go. If we connect this to enthalpy, and this is not the only way that we should look at it, but think about it this way: as an exothermic reaction generally would want to be spontaneous, and an endothermic reaction is generally one that would not be spontaneous, something we have to pump energy in to make it go. So if we look at these two reactions, which are basically just the reverse of each other, we have hydrogen and a hydroxide, and hydrogen ion and hydroxide going to water. Delta H is minus 56.2 kilojoules per mole, or kilojoules for the reaction. The reverse, we change the sign. This is exothermic, this is endothermic. This is spontaneous, this is non-spontaneous. Entropy. We've talked about enthalpy, the heat, the energy involved in bonds. As bonds reorganize, that energy that is involved is enthalpy. Entropy, on the other hand, is a measure of disorder. If we have low entropy, we have low disorder. We have a more highly ordered system. If we have high entropy, greater disorder. Entropy is related to the probability distribution of microstates. Now that, I'm sure you all understand what that is anyway, but I'm going to talk about that just a little bit more in a couple of slides coming up. So here's one thing about entropy. When we were talking about delta H, if you look up in table 2, in appendix 2 in your book, you'll find that elements, their standard enthalpy of formation for an individual element, it's always 0. An element in its standard state, 25 degrees C, 1 atmosphere of pressure. Delta H for an element, the enthalpy of formation for an element is 0. That is not true for entropy. We cannot know absolute enthalpy. We don't know how much heat is involved within something, but we can know how much disorder is within something. So that is a very key distinction between enthalpy and entropy, is that we can now know absolute entropies on the basis of the probability distribution of microstates. Remember that entropy is just disorder. Okay, so here we go and look at microstates. So what we have here, we have 2 containers, 2 atoms, 2 different atoms. 2 spaces, 2 regions of space, 2 different particles. There are 4 different possibilities for the microstates. We can have both of the, we can have both atoms on the left. We can have purple on the left, yellow on the right, or reverse. Or we can have both atoms in the chamber on the right. So the number of microstates, if we organize it this way, we get a statistical distribution of how those particles can be, where they can exist. Each of these individual scenarios is a microstate. So as here we're only looking at 2 atoms. Now think of what this would be if we had 4 atoms. We have a lot more possibilities for the numbers of microstates. What if we have 10 atoms? What if we have 100 atoms? What if we have 1 billion atoms? What if we have a mole of atoms? The whole concept of working with this is called statistical mechanics. This was really studied by a guy by the name of not Erwin Schrödinger, by Ludwig Boltzmann back in the late 1800s. Boltzmann was a physics professor at the University of Vienna, and he is the one who did a lot of work in this area. And his work was groundbreaking at the time. I mean, something like this doesn't maybe seem so complicated with a simple model. But at the time, in the 1880s, remember your timeline, John Dalton, 1808, published his paper on the idea of atoms. The smallest particle of any element that you could have would be an atom. People hadn't really accepted atomic theory at that point. Many people still felt that matter was continuous, including most of the contemporaries of Boltzmann at the time. So in professional circles, Boltzmann was widely criticized and even ridiculed. Among other people, particularly a guy by the name of Ernst Mach. And if you are familiar with the name of Mach, who is connected with the speed of sound, Ernst Mach was a highly respected professor in Germany. He had his little tribe of people that believed the same way he did. They were not atom people. And he pretty much destroyed Boltzmann's career. He really went after him and attacked him about his theories that were based on the fact that atoms existed. So Boltzmann, who was a brilliant young scientist coming up, a professor doing research at Vienna, he also suffered from mental health issues, took a 2-week vacation and from his job and committed suicide in his early 30s. So just one of the many stories that you find behind the development of science historically. Now, as I talked about perhaps a mole of atoms, Boltzmann came up with this particular equation for calculating the total number of microstates, which is W. W represents the total number of microstates. X would be, let's say, the number of pods or chambers where those atoms can be, raised to the n. So remember what I mentioned, what if we went from 2 atoms to 4? Well, that pretty much squares the number of microstates possible. What if we increase this by a factor of 10? What if we increase this by a factor of 1,000,000 or a mole? You can see that there are an incredible number of microstates that one can generate from this. For all practical purposes, I am not going to be interested in the fact that you know how to use this. I mean, you can use this equation. It's a very simple one. I am more concerned about how this connects with entropy and overall disorder. And here's how it connects. S is the absolute entropy. It's the absolute measure of disorder in something, in anything. So if I hold up my lovely Bethel University water bottle, there is a certain amount, a measurable amount, a knowable amount of entropy in this container. Okay, I have a little water in here, but let's just talk about the container by itself. So S is absolute entropy, a known quantity of disorder. K is a constant connected with this called the Boltzmann constant, named after Ludwig Boltzmann. And W is the total number of microstates that are involved. Okay, so here's what you need to know about entropy generally. Nature tends toward increasing disorder. Let's say you get up in the morning. You roll out of bed. When you come back, if you don't do anything, if you come back at the end of the day, is your bed made? Now, without somebody doing it, if anything, your bed left by itself may collect dust. It may, maybe your roommate comes and jumps on it or something like that. With time, nature trends toward increasing disorder. Not just stays the same. Nature tends toward increasing disorder. Just think about something that's static. Let's say you take a can, set it outside. Nice and shiny, brand new. Give it a year. You look at that can. Maybe it's beginning to rust. Maybe it's discolored a little bit. Nature tends toward increasing disorder. It doesn't just stay the same. Things decay. Things fall apart. things chemically react. If entropy is increasing, now for the first time we're looking at delta S. Delta is the change in entropy. If entropy is increasing, delta S is positive. In other words, nature tends toward disorder. Delta S being positive, that wants to happen. That is a spontaneous change. If entropy is decreasing, delta S is negative. Remember our little knot, our little zero here? That stands for standard conditions. 1 atmosphere pressure, 1 molar concentrations, 25 degrees C. 25 degrees C or 298 kelvins. Standard temperature is 298 kelvins in thermodynamics, not the gas laws, but in thermodynamics. So if entropy is decreasing, one has to put in work in order to create more order. So it takes work to make your bed in the morning. It takes work to clean your room. It takes work to do dishes because things tend to go toward disorder. All right, so I've just covered the first 3 sections of chapter 15. Did you get all that? Wasn't that brilliant? Yeah, not really. All right, so here's what you need to know. Just like, here's what we're going to treat with regard to delta S, and this is for a system. This is for a system. Remember that can example? We set it outside. The system would be the can. Everything else could be the surroundings. The change, like everything else that we've talked about, is final minus initial. Some final state minus initial state. That's the change that occurs. Standard conditions. For a chemical reaction, delta S is just like delta H. It is the total entropy of the products minus the total entropy of the reactants. Qualitatively, you can also qualitatively predict the sign of delta S for a system. And that's what we're going to be talking about here next. Okay, degrees of disorder. Let's talk about 4 states of matter: solids, liquids, gases, and solutions. Solids. I don't know if you can see this well. You can go back and look at the slides. The solids, let's just think of an atomic solid, like a metal. So in a metal, the atoms are close together. The atoms are locked in a lattice. The atoms are not moving freely. They are locked into a position. At room temperature, there's a little bit of vibration due to thermal motion. But the thermal motion occurs. Those atoms are touching one another. They are locked in place. There is not much disorder because of those atoms being in a rigid lattice. Solids versus a liquid, a solid has much lower entropy than a liquid. There's more order in a solid or less disorder in a solid. In liquids, the molecules are in constant contact, but now they're moving past one another. Still touching, but now there's more free movement. And because of that greater movement, more disorder for liquids than solids. In the case of solutions, think of a solid added to a liquid to create a solution. Whenever you create a solution, there is always more disorder than a solid and liquid individually. Because now the solid, which was locked in rigid, those particles are spread out and they are moving freely throughout the solution with the liquid in their hydration or solvation sphere. So solutions have more disorder than either of these two. And finally, gases have a huge amount of disorder. What do you know about gases? All right, come on, I'm waiting. You can tell me. Rapid random motion, perfectly elastic collisions. The particles have tiny volumes compared to the space they're in. There is a tremendous amount of disorder in gases. Here's solid. Here's a transformation from a solid to liquid. Can you just see the increasing disorder in this liquid over here on the right? Well, it just looks like a pile of atoms. Solid to gas. Here you've got particles that are adhered together, and now it's like they just blew apart. Solid to solution. The solid, now that it's dissolved, there's much more disorder in this particular thing. Even a solution has more disorder than a pure liquid. What if we heat something? What happens with disorder? As you heat anything, the molecules are moving more quickly. That's how we define heat and temperature, really. The particles have greater energy, greater kinetic energy, more movement, greater average kinetic energy. So as we heat something, it's getting more disordered. So delta S is becoming more positive, delta S is increasing. So let's do this quickly. Positive or negative entropy change. Melting, positive or negative entropy? Positive, negative. Melting, solid to liquid. Entropy is increasing, positive delta S. Vaporization, liquid to gas, increasing disorder, positive delta S. Dissolution, a solid dissolving into a liquid. Entropy is increasing, positive delta S. Freezing, the opposite of melting, a liquid condensing into the solid state. Delta S is negative. Disorder is decreasing. Sounds like a double negative. That's why it can be confusing. Entropy is decreasing because disorder is decreasing. Heating, heat it up, increasing disorder, positive delta S. Condensation, vapor to liquid, delta S is negative. Okay, let's look at these chemical reactions and predict the sign of delta S. Let's just pause and look at the first one for a moment. Iron plus oxygen forms Fe2O3, the rusting of iron. Okay, let's just look at this first reaction. Here's how to determine whether delta S is increasing. We have solid, gas, and on the right side, solid. Which side has more disorder, reactants or products? Well, yeah, that's obvious. All this gas over here, no gas over here, there's much more disorder on the left. So as we go from left to right, as this reaction proceeds, disorder is decreasing. Disorder is decreasing. In other words, we're forming a more ordered product than reactant. So delta S will have a negative sign. We don't know how much, but we can predict that we can be sure that delta S is negative because we're creating more order in the system. Look at the second one. Gas, gas, gas. Everything's a gas. Right. Not going there. Entropy. Everything's a gas. Does entropy stay the same? Well, not really, because now it depends on how much gas. Here we have 1 mole of nitrogen, 3 moles of hydrogen, and 2 moles of ammonia. On the left side of the arrow, we have 4 moles of gas. On the right side of the arrow, we have 2 moles of gas. We're going from 4 moles of gas phase reactants to 2 moles of gas phase products. Is entropy, is disorder increasing or decreasing? That's right. Entropy is decreasing because we're going from 4 to 2 moles of a gas. Delta S will have a negative sign. 4 moles to 2, that's creating more order. Let's look at the third one. 2 moles of gas, 2 moles of gas, plus 1 mole of gas. 2 moles of gas going to 3, entropy is increasing. Positive sign of delta S. 6 moles of gas, 6 moles of gas, 1 mole of solid, 6 moles of gas. 12 moles of gas on, just ignore the solid. That entropy isn't even going to matter here because gases are so much more disordered. We have a total of 12 moles of gas on the left, 6 moles of gas on the right. Entropy is decreasing, going from 12 to 6 moles. On the left, 4 plus 1 is 5. Liquid, solid. We don't have to go any further than this. We have gas on the left, none on the right. Entropy is decreasing. Negative sign of delta S. Gas, 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 gas. Now we have to look at how many moles. On the left, we have 15 moles of gas. On the right, we have 18. 15 moles of gas going to 18 moles of gas. From a disorder standpoint, entropy is increasing by a little bit, by 3 moles of gas. Delta S positive. So from what I've just said, if you want to go back and review these slides, here are the answers that we just walked through and why. So you can practice with these later on your own. Now, let's talk about chemical reactions a little bit more. In order to find delta S for a reaction, we approach this just the same way we did delta H. Do you remember what we did with delta H? Good, I'm glad, because it's the same process. You look up the values in the appendix, appendix 2. S has different units. This is now joules per mole Kelvin. What are the units for delta H? Joules or kilojoules? Come on. That's right, kilojoules. Delta H is kilojoules. From the table, kilojoules per mole. For entropy, it's joules per mole Kelvin. There's a temperature term in there. Elements have an entropy value. For delta H, remember, in enthalpy of formation, all of the delta H values are 0. Entropy, however, for elements will not be 0. There will be some number there. And all of the entropy values from the textbook are going to be some positive value because it's related to the disorder that something has at room temperature. It will always be a positive disorder value. So products minus reactants, multiply coefficients by entropy for each component, products minus reactants, you find delta S. For delta S, the units for a reaction, not from the table it's joules per mole K, but for a chemical reaction, like the 6 reactions we just looked at on the previous 2 slides, joules per Kelvin. Joules per Kelvin. The moles cancels out. Remember, we multiply the coefficient, which is the number of moles of that thing in reaction. Moles times kilojoules per mole gives us joules per Kelvin. Here's an example. This is the first reaction on that previous slide. We look up the entropy values from the appendix. Element, delta H would be 0. Not entropy, 27.2 units, joules per mole Kelvin. Oxygen, look at this for a minute. This is for 1 iron. This is for 1 mole of oxygen. The oxygen has almost 10 times the entropy as the iron. Does that make sense? Gas versus solid. And now we're back to a solid. But this solid is more complicated than this solid. This solid has more disorder. It's much bigger. This atom, or this molecule, only has 2 atoms. This molecule has 5, or the formula unit has 5. 90, these numbers you either have to be given or you look them up. How do we calculate delta S? Let's just look at it empirically before we go down here. 2 moles times 90 joules per mole K. Products. Products minus reactants. Minus 4 times this, minus 3 times this. And that's what I've just laid out here. When you pull all of this together, this is the total entropy of the product side, the entropy of the reactant side. Make sure that you remember this little negative sign here. And then we get our overall delta S for this reaction. Did we say entropy was increasing or decreasing? Yeah, it's decreasing. Solid plus gas goes to solid. It's definitely decreasing. This is how much it's decreasing. We can quantify that. So for this reaction as it's written, that is the entropy change for the reaction. Okay, that is it. So we are going to pick up with the rest of chapter 15. Yeah, 15, that's where we're at. We're going to pick up with the rest of chapter 15 on Friday. So until then, make sure that you get those worksheets done and do the quiz. All right.